Uh, update on your fundraising goals. So thanks to Mr. Fullerton and one of my former students who donated to your class in the name of Ryan Fullerton, you all are now up to 150 bones. So still well behind second block.
Ryan needs in.
He's so demanding. I need in, I want to learn. Hi, Mr. Fullerton.
I just thought you didn't like me or something.
No, you asked everybody, I'm going, where's Ryan? It's unlike him to not be in the meeting. So I hadn't seen your invitation to want to join, so that's not on me there, big boy.
You can ask Joss as an
Nope,
eyewitness.
nope,
I
nope.
asked him at
It's all lies.
1:18.
It's all lies, okay? Fake news, okay? Make physics great again. No. Okay. All right. So that's what we got to have. MPGA, make physics great again. Okay. Or maybe just science. MSGA, make science great again. There's our fundraiser. We'll sell t-shirts and have that as bumper stickers. Money goes to the Solar Foundation. Make science great again. Okay. Anyway, so back to our story. All right. So does anybody have any specific questions on that assignment from Friday?
Number 8 from your questions.
Is that with the crane and the bucket?
Yes.
Okay.
I think I overthought it and complicated it.
Don't. Okay. So here's the bucket, and it has dirt inside of it, oddly enough, right? So you have to lift two things. You have to lift the bucket and the dirt that's inside of it, right? So you have the weight of the bucket. You have that number. You don't have the weight of the dirt. But you know the density is mass divided by volume. So you've got the density, you've got the volume. Multiply those two together, that's the mass. Then, to get the weight of the dirt, you multiply that by G. So the weight of the dirt, okay, it sounds like a really bad physics gang, but it's rho VG equals the weight of the dirt. So, yeah, what are the rho VGs? So here's your density, here's your volume, so those two together get you the mass of the dirt. Multiply that by G, there's the weight of the dirt. Add that to the weight of the bucket, multiply that by the height, that's how much work you're going to do. So your answer to 8A should be something times 10 to the 5th. Okay? Something times 10 to the 5th. Then on B, you want to calculate power. So power is work divided by time. So in situation number 1, you're going to lift it in 2 minutes. The next situation, you're going to lift it in 1 minute. Okay? And what you'll see is that the faster you lift it, the more power that requires. Okay? Gannon, did that answer that question?
I read the V as velocity.
The units don't work out, man.
You know, in my head,
No,
I had it rationalized.
no.
A bird would know what he's doing.
No. Why would I give you a new formula where I have mass divided by velocity? You get kilograms? No.
It's also capital V.
Oh,
Same mistake again, I'm just saying.
It is a capital V.
I'm trying.
Josh mocked me profusely while I was asking for help. He said you need to slow down and think about it, and I should have slowed down and thought about it.
Which is true of many things in life. True of many things in life. Okay. Anything else?
Can we go over number 6 in the book?
Is that what it's like, pushing it up an incline?
I think so.
It's got like a 20-degree angle. Here's the box. And this is like the 68 Newton force. And there's 20 degrees. Okay. So here's the story on number 6. okay? Here's what you have to understand. When you're calculating work, the only force that you consider is the force that is in the direction of motion. Okay? Listen to me. It's only the force that's in the direction of motion. So I'm not going to use that 68 Newton force, okay? Because it's like this. Here's this block, right? And I'm trying to push it up my arm, but I'm applying a horizontal, but I'm pushing like this. But the only force that I consider is this side of it, okay? So this is going to require a little bit of trig. So you want to find this side of the triangle, right? So if you look at it, this is actually the hypotenuse, right? So here's this 20 degrees, here's the hypotenuse, you know this side over here, so you know the side adjacent. You know the side adjacent, you know the angle, find the hypotenuse. Now, think this through. Does this side over here, because it's the hypotenuse, is that going to be bigger or smaller than 68 newtons? Diego.
It's gonna be bigger.
It's going to be bigger because it's the hypotenuse. Hold on. Okay. I thought that camera had stopped working for a second and I was going to flip out. It's good. It's still going. Okay. And then once you get that force, then you're going to multiply it by the length. Now, here's your force. You know, and then you have to look at, is the force in the direction of motion or is the force in the opposite direction of motion? On number 2, on those problems, you want to make sure that you've got these diagrams, okay? And again, you only consider the force that's in the direction of motion, okay? So when you're doing these calculations of work, you're only going to use these sides of this triangle if you're lifting something up, okay? Because that's the only force in the direction of motion, okay? So like on number 2, on number 1, that work should, for that first tension should be around 8,000 joules, and that second one should be around 4,500 joules. And you also have to pay attention to the sign. Which direction is this thing? Is it moving up or is it moving down? Okay? Make sure on my questions on number 11 that you have given some type of mathematical justification, and you cannot say, oh, because it has a bigger acceleration. Just because something has a bigger acceleration is not a justification for why it's going faster or why it has more momentum or why it has more work done on it. Okay? Just because something has a bigger acceleration is not a justification. Where does that acceleration play into an equation? That's how you want to address those on number 11. And your answer to number 10 would make a not so good GPA. All right. Are we good on that assignment? Hold on. Let me see what's on the chat. Okay, we got number 6 in the book, so we got that one done. Okay. What?
On number 8, B and C, can you have a negative answer, like negative watts?
On mine?
Yes.
On number 8?
Yeah.
No, those are positive. Because you're lifting the bucket up. If you were lowering it down, then it would be a negative value. Okay? Yeah, all of your answers on number 8 are positive values. Now, you should have some negative answers on this assignment, but number 8 isn't one of them. Okay? All right. Anything else? Going once, twice.
Wait, so friction has negative work, correct?
Yes, because it's in the opposite direction of motion.
All right.
Yes, this is true. You speak words of truth, Gannonberg. Okay. Anything else? Once, twice sold? Okay. So, make sure I get that assignment today. All right, so here's the next big thing. And that's energy. So here's the weird thing about energy, okay? Everybody knows what it is, okay? But it's hard to, if I said, all right, don't do this, okay? But if I said, okay, I want everybody to go into the chat, and I want you to write out a definition of energy, okay? If I said, what is the definition of energy? I think you kind of have to struggle with that. It's like, huh. You know, if some alien lands and you go, hey, you all are having to, and this alien is going, hey, what are some of the things you guys are talking about? And you say, well, we're talking about energy. And the alien goes, well, what is this energy you are debating? It's like, how would you explain it to the alien what energy is? So here's the deal. Back when I actually taught you all in this classroom, I could get an idea of how much energy you had when you all walked in, okay? Josh Avery, right? He was pretty even keel. I knew Josh when he would walk in, probably wearing the Hawaiian flowery shirt, right? That would be about as much energy as I would get out of Josh. Josh is pretty even keeled, right? He'd walk in, sup, okay, right? Lauren would typically walk in and have a lot more energy, okay? Because she goes, oh, just got out of swim meet. Oh, I saw the moon. Ah, okay, look, I have popcorn, okay? So Lauren would, on average, would tend to have more energy than Josh, okay? And so I could look at your interaction and get an idea of how much energy that you guys have. And the same thing with me, okay? Wow, what's Burkhamp's energy level today? You know, is he pretty laid back? You know, he's not feeling so well. How's Burkhamp doing today? So you can sense it, okay? But as far as quantifying it goes, that's a little bit more difficult. So here's, from a physics perspective, okay? Energy is the capacity to do work, okay? So let's just think this through. So let's say it's Saturday morning, and Aunt Martha is coming over to the house, and your mom wants the house cleaned up, because Aunt Martha will gossip if it's not, okay? And we all know, we all have an Aunt Martha, okay? And your mom goes, I am not going to be the subject of ridicule on Facebook, okay? I'm going to have this house cleaned. So she goes to Diego. She goes, Diego, come on, get out of bed. I need you to go run the vacuum cleaner. So Diego's mom is asking him to do work. She is asking him to exert a force through a distance and do work, okay? Now, if Diego says, from a pure physics perspective, he goes, Mom, I got no energy, okay? I got no energy. What Diego is saying from a physics perspective is that he is incapable of doing work. He is incapable of exerting a force through a distance to run that vacuum cleaner. Okay, that's what he's saying. If you say, I got no energy, you're saying, I do not have the capacity to exert a force through a distance. Okay, that's what you're saying. Okay, that's what you're saying. Now, so energy can take on a whole bunch of different forms. Okay, and so it's this kind of nebulous thing. So the two broad types of energy that we're going to talk about in this class is going to be potential energy, and we're also going to be talking about kinetic. So, in terms of potential energy, we're going to be dealing with gravitational potential energy, which is going to be UG. So gravitational potential energy, any potential energy is shown by the letter U, okay? So that's going to be UG. So that's going to be gravitational potential energy. So if I take ET and I lift ET up, I have stored gravitational potential energy. Now, UG is going to be mgh. The mass times g times h. Now, the other thing that you'll see is that energy doesn't have a direction. Energy is a scalar quantity because of the fact that you just have energy. I don't have energy directed in a particular direction. Lauren walks in going, "Hi, Mr. Rickett," okay? She has energy, but it's just this kind of nebulous glow around her, right? She doesn't have energy in a particular direction. Oh, now she goes, "Hey, I'm going to walk towards you." Oh, there's momentum. Boom. That has the vector quantity. But energy is just, okay? Which is a highly technical term. So, UG, we're going to spend a lot of time talking about UG. You can also have US, okay? So US is energy stored in a spring. Okay, so this is going to be later on, we're going to talk about this. So US is, don't worry about this equation for now, we'll deal with it. So K is the, hold on, I got to get something that I dropped. Give me 1 second, I'll be right back. I dropped my penguin. He was a victim of gravity. So, if you talk about energy stored in a spring, so within this little launching mechanism, there's a little spring. So, when I push this in, I do work, okay? I did work because I stored potential energy, I exerted a force through a distance. Now, when I release that energy, okay, it turns into a projectile. So here's the deal. I do work because I exert a force through a distance. I have stored US. Now, because it's up above the ground, I also have UG. Okay? So now when I release this, it's going to have two types of energy. Stored energy in the spring and potential energy because of gravity. So when I fire it, okay, then now I'm converting two types of energy. UG, because it's gravitational, and it has US, because it's going to be shooting that thing out. And what you'll see in that perfect example right there is that Mother Nature does not like potential energy. Mother Nature much prefers kinetic energy over potential energy. They said something about each other on Twitter, Snapchat. Somebody made an inappropriate TikTok video. I don't know. All I know is that Mother Nature and potential energy don't get along. Mother Nature much prefers kinetic energy. Now, the third one we're going to deal with, and don't worry about this for now, is going to be UI, which is electrical potential energy. Okay? This one we will get to in the spring. Okay? So this is like if I take two charged balloons that are negatively charged and I push them together, that stores potential energy. Then when I let those balloons go away, they go flying apart. So this one we'll get to in the spring. For now, all you have to worry about is UG and US. We'll deal with the other ones later. We'll deal with UI later. Now with kinetic, you're going to have two types of kinetic energy. Translational kinetic energy, which is 1/2 mv squared. And then you're going to have rotational kinetic energy, which is 1/2 I butt squared. Okay? Now, here's the cool thing about these two types of energy. This is mass, which is a reflection of inertia. This is moment of inertia, which is resistance to a change in motion. Okay? So this is inertia, this is inertia. This is how fast you're going. This is how fast you're spinning. Notice that they're both squareds, okay? And they're both 1/2. Now, if you look at this from the units, okay? If you look at this from the units. So let's start with UG, okay? UG is mgh. Well, that's kilograms meters per second squared times meters. So I got kilograms meters times meters over second squared. I get kilograms meters squared over second squared, which is the same thing as Newton meters, which is the same thing as joules. Okay? So UG, I get joules. US, 1/2 kx squared. Later on, you'll see that this k has values, this k has the units of Newton meters. And then if I multiply that by meters squared, then one of those meters cancel out. I get Newton meters. That's the same thing as joules. Over here on the kinetic energy side, I've got kilograms times meters squared over second squared, which is the same thing that we ended up over here. And then you can have rotational kinetic energy, and that I on I omega squared. Remember, moment of inertia is kilograms meters squared. Rotational energy is radians per second, but that gets squared. So I get kilograms meters squared per second squared, which is that exact same thing. So all forms of energy end up in joules. So even if you look at Einstein's equation of E equals mc squared, okay, he goes, oh, it's brilliant. Look, it has to be mc squared. That's the only way you can get the units to work out. He couldn't say, oh, energy is mc, because all the physicists in the world are going, hey, Al, you're an idiot. If you multiply mass times the speed of light, you just get momentum. The only way the units work out is that it's c squared. Okay, that's it. That's the only way. Now, his genius was figuring out that there's nothing out here in front of it. Okay, there's no 1/2, there's no pi, anything like that. It's just mc squared. And we'll talk more about this equation later. Okay, so if you look at what's going to define your generation, okay, let me give you some historical perspective. So my dad was born in 1927 out by what is now Cheney Lake. And when Dad would come into town, into Wichita, 21st Street was a set of wagon ruts. Okay, that was it. So when he was a kid coming into town, they would hook up the horse to the wagon. They'd drive into town from Cheney Lake. It would take all morning to get into town. They'd do whatever shopping they need to do, and then they'd go back home. It was an entire day-long trip, okay? Because 21st Street was a set of wagon ruts. That's all it was. Now, my dad died in 96. So from 1927 to 1996, my dad saw a huge transformation in how we move. So Dad went from seeing a horse-drawn carriage to get into Wichita to walking on the moon, to the space shuttle, to international flights on jets, okay? Wasn't any big deal. So my father, in the 69 years that he was on this earth, saw a huge transformation in how we move, okay? More so than any other generation. My generation has seen a huge change in how we communicate. So, to give you some perspective, growing up in Cheney, we used to have what was called the party line, okay? You had a private line and you had a party line, okay? There was two different types of telephone service you could have. So us kids had a party line. So what that means is that that phone number, when you would pick it up, that line was shared like 3 or 4 other households. So this is, you talk about no privacy, okay? So you'd pick up the phone and you'd wait for the dial tone, or you'd have to see if somebody else was talking. If somebody else was talking on the party line, you had to wait until they got done before you could dial. What that also meant was that you had to be careful about what you said on the phone, because you knew there were 3 or 4 other people that could be listening in on your conversations. So you really had to be really careful about what you said, and you couldn't tie up the line for very long in case somebody else needed it, okay? Now, if you had the private line, you were the only one that was on that, but you had to pay extra for the private line, okay? We also had the old rotary dial, okay, where you put your finger in and you'd spin the dial, okay? That's how you used to call. I remember in 4th grade, Mike Denny, good friend of mine in 4th grade, Mike Denny's family was the first one that had the telephone and had push-button dials, okay? That had push buttons instead of the rotary dial. We went over to his house after school to push buttons on the phone, because that was the coolest thing that we had ever seen. Like, oh my God, he's got a push button phone. How cool is this? He is also the first to have the video game Pong. Okay? Have you ever seen Pong where it's got a little ball that bounces and you slide the deals up and forth? That was the first video game. So Mike Denny had the first push button phone and the first video game. We were so jealous. It's like, oh my God, it's so cool. Okay. Now, when, like in my junior research paper in high school, there was a library. You had to go there and you had to like open up books, okay? And you had to write stuff down. And you had to like physically type the paper. You couldn't just, oh, I'll just cut and paste it from a source. No, you actually had to write it down. You went to the card catalog, okay, and you found that magazine and you would go actually grab the magazine and open it up and read it and write down the summary. I know you'll find this shocking. You're going, Mr. Burkamp, what is this evil that you speak of? Okay? Yes. Now, and then we had cell phones. Okay? This was the time BC, before cell phones. Okay? Then cell phones came like, oh, great, this is earth-shattering. And you had the bag phones. It would only work when the phone was plugged into the car. That's the only time the phone would work. Okay? Sometimes it had a little bit of battery life, but not much. So if you look at, and then we got the internet. Okay, that was even cooler, right? Oh, the internet. And then I remember when we first got the internet at the school, we had one computer that was hooked up to the internet. And we'd go in and we'd take turns doing a search on the internet. Okay, like we could pull up the weather. And it was like, oh my God, this is so cool, right? And then the internet became on your phones. And now it's like, hey, you know, now you can just ask your phone. You don't even have to do anything. It's like, hey, Siri, what's the 22nd Amendment? Oh, okay, the 22nd Amendment is da-da-da-da. So my generation has seen a huge transformation in how you access information. You have a smartphone. You have access to more information than any other generation that has ever been on this earth. Okay? But with that comes responsibility. Okay? Because just because you have access to the information, you know, doesn't mean that people know how to use it correctly. And that's the struggle. Now, this is what I think is going to define your generation. Okay? My prediction is what's going to define your generation is energy. Look at how the bad thing about the internet and everything else is that we are so absolutely dependent upon energy. We are more dependent upon energy than any generation that has ever lived on the face of this earth. Okay? We are. Look at Dillon's, okay? Right? Nothing is growing at Dillon's. Okay, they might fry the chicken or make a salad there, but that's about it. Everything gets shipped in. Look at the availability of electricity. We lost electricity here, what? Well, right before Thanksgiving. We had to shut the school down because we didn't have electricity. Look how dependent upon you are on the internet. Look at how dependent you are on UI. Look at this in terms of your phone. Imagine how your life would change if your phone only worked when it was plugged into the wall and we hadn't developed batteries. Okay? Imagine that your cell phone only worked if it was plugged into the wall. You'd be going, oh my God, Mr. Burkamp, what is this evil you speak of? Yes, imagine that. Imagine if you go to start your car. I don't know if you've ever seen the footage of the old cars. How you used to start a car, you had a crank that you would put in the front of the car and you would turn it over. So your potential energy was stored in your muscles, and that's how you would start your car. So imagine, if you will, that we hadn't invented batteries. Oh man, I got to start my car. Okay, get the crank out, put it in the engine, boom, crank it over. Okay, because you would be the human battery. So your generation is built upon cheap, readily available energy. And we're very, very dependent on it. The question that's going to face your generation, how do you get that energy? Okay? So if you look at the solar project, which is pretty cool, right? So within an hour, if you could harvest all of the energy that hits the sun, that hits the earth from the sun in 1 hour, if you could somehow harness all of that energy, that would be enough energy to power the world for a year. Okay? We get that much energy from the sun. If we could take 1 hour of energy from the sun that strikes the earth and somehow harness that, all of that energy in 1 hour and store it, we could power the earth for a year. That's how much energy we get. So that's the cool thing about solar panels is that, okay, hey, that energy comes in, it strikes the solar panels, we convert it into electricity, we ship it here to the school, hey, I can make toast. So whether that's wind, whether that's solar, whether that's battery storage, that's what's going to face your generation. And you can continue to produce it by burning coal, burning natural gas, whatever. Downside of that is you're producing tons and tons and tons of carbon dioxide. So that's the challenge that is going to face you guys. How do you have an abundant supply of cheap energy, but yet at the same time cut down that carbon dioxide production? That's what's going to challenge your generation. Okay, so if you look at a simple transformation, so I'm going to spin the camera over here for a second, okay? So give me a second. Oh, da-dee-da-da. Da-da. Okay. Can you all see? Yeah. Okay. So what I have here is a weight suspended by a string from the ceiling. Okay? All right, so I got this, right? So what I'm going to do is that I'm going to lift this up, right? Okay? Now, when I lift it up, I do work because I'm exerting a force through a distance and I'm lifting it up. Now, when I let go of it, Mother Nature doesn't like potential energy. So as soon as I let go of it, that potential energy is going to begin to change into kinetic energy. So it goes from potential energy here, down into all kinetic energy here, back to potential energy here. So it's just this continuous transformation from one to the other. Now, if you look at how you determine UG, right, MGH. So if you look at this in terms of, here it is at the bottom. So if I lift this thing straight up, I do a certain amount of work, I store a certain amount of potential energy. Now, if I lift it up like this, where it has that exact same change in height from here to here, that's the exact same amount of potential energy that I'm going to store. Whether I lift it up, straight up like this, or I put it over here, it's going to have that same amount of energy no matter what. So, I've got potential energy, kinetic energy. Potential energy, kinetic energy. Now, so one of the ways you can look at this, I'm going to change this back over so I can write on the board. Okay. So, when I lifted that thing up, that's going to have a certain amount of UG. So you can think of this as being like a container. And we have one container named UG, and we have another one named translational kinetic energy. So, when I've lifted this up, I've got all UG. Right? Because when I hold this thing up, so when I grab this weight, and I pull it up like this, okay, and I'm going to hold it right up against my nose, okay, so I'm right here, I'm going to hold it right up against my nose, okay, then I'm going to let go of it. Okay, now, normally I do this down in the library with a bowling ball, and it's a lot more dramatic, but I can't get into the library, so I can't do this, so this is as close as I'm going to get. So, I got this chunk of steel, right, and I'm going to hold it right up against my nose. I'm going to let go of it. Now, I know there's no way that that block is going to hit me in the nose again. Because here's the reason why. I'm going to start with a certain amount of UG and no kinetic energy. So as it falls, imagine that there's a siphon, okay? Imagine that there's a siphon that transfers UG into kinetic energy. So as this thing gets siphoned off, UG is decreasing, kinetic energy is increasing. Now, when it's at the bottom of the swing, okay, here, it has all kinetic energy and no UG. But then when it starts to go back up, then I'm going to transfer some of that kinetic energy back over to UG. Now, eventually, we have to talk about a third container, and that's going to be thermal energy. Because what's going to happen, if I get this thing going, right, okay, I'm going to hold it right up against my nose, okay, I'm going to let go, okay. Even in this little bit of time, you'll notice that it doesn't swing up as far. It doesn't swing up as far because as it's moving through the air, it's colliding with the nitrogen and oxygen molecules. We're losing some of the thermal energy. So eventually, all of this energy is going to get transferred over here to the thermal energy, and the air in the room is just going to be a little bit warmer than when it started. Because as that moves through the air, it's going to collide with those particles, and it's going to generate a little bit of thermal energy. Now, don't sit there and go, oh, man, it's cold in the house. I'm going to go let a ball swing back and forth. I'll warm up the house. No, okay? No. It's going to generate such a small amount of thermal energy. But if you go really, really fast, like a spaceship coming into re-entry, like the Apollo missions, when they returned from the moon, they had a tremendous amount of kinetic energy that when they hit the atmosphere, they would heat up, and then you would take that energy and change that into thermal energy. And that's why it was so dangerous on re-entry, because you were transforming kinetic energy into thermal energy. So here's what's most important. The amount of energy in the universe is a constant, okay? And it just changes forms. So, and somebody was really, really bored. And they determined that if you've ever seen like the movie Monsters, Inc., where they harvest the energy of like screams or laughter, okay? So somebody did the math, and if you screamed like this, ah! Okay, so if you could do that for like 10 hours, okay, and you could harness that energy, you could make a pot of coffee, okay? If you could harness the energy that came from sound. But the problem is that energy becomes so diffuse. Now, this is why I like to, even in the remote setting, this is why I like to teach in this room. Because the amount of energy that you all brought into this room still exists within this room. Okay? Because the amount of energy is constant. So when Lauren laughed, okay, there was a certain amount of energy in the room that was still there. Okay? When Gannon would go, oh, I forgot to do that, okay, and he would kind of flip out, right? That energy is still here, okay? When Joelle would sit over there, and I can't do this, and she'd like cross her legs. If I tried to cross her legs like Joelle did, you'd have to call the paramedics, okay? But every time that she would like cross her legs or kind of shift in her chair, there was a certain amount of energy that was in the room. And that energy is still here. So all of the energy from all of the years of teaching in this room since the fall of 1996, okay, 24 years, the amount of energy that was in this room from laughter, from tears, from talking, whatever, it still exists in this room. So that's why I like to teach in this room, because I'm still thriving on that energy. Okay, now, here's how work and energy play into this. So, on your equation sheet, you have, let me find it. Okay, so on the yellow sheet, and it's the most nebulous, weird equation that you're going to have, but it's the most intense. So, change in energy is equal to work, which is equal to force times distance, which is FD cosine theta, okay? So here's the deal. force times distance. The reason they do the FD cosine theta is because you only consider the work in the direction of motion. That's the only reason that's there. Don't worry about this, okay? Don't worry about it. Here's what you need to remember. The change in energy is going to be equal to work. Now, that change in energy could be kinetic energy, it could be potential energy, it could be UG, it could be US, it could be UI, it could be rotational kinetic energy. It doesn't make any difference. So, if you look at this in terms of work, so here I've got ET, right? So here I've got ET. Now, ET has this little spring on the side of him, okay? So I'm going to wind up ET. Now, when I wind up ET, I'm doing work because I'm exerting a force through a distance. And I'm storing energy within the spring inside ET. Now, when I set ET down, can y'all see ET? Here, I'll put ET on a rock, okay? So now, when I let go of ET kind of gets the ET shuffle going, right? So ET is moving, right? So what's happened is that the amount of energy that I stored, the amount of work that I did, is existing as potential energy within the spring. Now, I let go. Some of that energy got transformed into kinetic energy. It was the energy of motion. You heard ET moving, okay? So you heard the gears turning. So some of that energy went into sound. The ET was moving, so there had to be some friction between his feet and the rock. So we lost some of that energy to thermal energy as well. But basically, when we get done, and here's what I don't want you to think. I don't want you to think that, oh, when he stops, all of that energy is stored back as potential energy. It's not, because if it was stored back as potential energy, it would just be a continuous cycle. I would wind up ET, he would go, and then when he stopped, oh, we stored that energy as potential energy again. Oh, then we could just reset him and he'd wind himself back up again. Okay, otherwise known as perpetual motion, which is against the laws of thermodynamics, which we'll talk about later. So when ET stops moving, okay, the amount of energy that I gave him still exists in the universe. Now, here's where this gets a little bit cosmic. The ultimate source of the energy for me to wind up ET is this big ball of hydrogen and helium that we have at the center of our galaxy. Excuse me, at the center of our Milky Way, not our Milky Way galaxy, of our solar system. Okay, got a little bit too cosmic on that one. So, because without the sun, there isn't plant growth. Without plant growth, I didn't get to have a chance to eat my Wheaties this morning. Okay? I didn't eat my Wheaties this morning and have milk from the cow that ate the grass that grew from the sun. All of this is going to stop. So even though it doesn't seem necessarily logical, but what's happening is that when I wind up ET and I let him go, the ultimate source of that energy is actually excuse me, from the sun. Okay. Now, so let's talk work. So work can equal the change in kinetic energy. And I'm going to write these as these broad ideas, which would be kinetic energy final minus kinetic energy initial. So K minus K naught. You could write that as 1/2 mv squared minus 1/2 m v naught squared. You could write that as 1/2 m v squared minus v naught squared. Okay? Now, here's one thing about kinetic energy. If I take this and I swing it back and forth, okay, even though it changes direction, the kinetic energy is always positive because it's 1/2 mv squared. So this is why kinetic energy is a scalar quantity, because even if I have a negative velocity, it gets squared, which makes the kinetic energy positive. Now, I can't have negative kinetic energy, but I could have a negative change in my kinetic energy. Okay? So if I take this and I stop it, I just did work. I exerted a force through a distance and I stopped that from moving. So if that situation, so this thing is moving, and then I stop it, I did work because I exerted a force through a distance to stop that weight, and I would do negative work because my final velocity minus my initial velocity would be a negative value. So I can't have negative kinetic energy, but I can have negative change in my kinetic energy, which means that I can have negative work. Okay? That's one of the key things that you want to look at. Now, the same thing is going to be true. If I grab this thing and I lift it up, I did work. And the energy that I store here, when I let go of it, so however much energy that I store here is equal to the amount of kinetic energy that it's going to have at that bottom of the arc. So it's very possible to have both kinetic energy and potential energy at the same time. So, if you look at earthquakes, okay? So the east side of Wichita has had like 4 earthquakes since Thanksgiving, all right? We never had to worry about earthquakes in Thanksgiving, or excuse me, earthquakes in Kansas. And I distinctly remember the very first earthquake that I felt. It was back in the fall of 2011, okay? It was a Saturday night. K-State was playing Oklahoma State in football in Stillwater. I was laying on my couch watching the game. And I felt the whole house move and the couch. And it was the weirdest thing because I'd never been through an earthquake again before. Fall of 2010, fall of 2011, very first earthquake that I ever felt in my entire life. So what happens is that it's all about energy. So you have energy stored within the crust of the earth, usually at the fault lines. Okay? San Andreas Fault is the classic one out in California. So you have these fault lines and it's storing potential energy. Something shifts and it begins to slide. So now you're taking potential energy at some fault line and changing that into kinetic energy, which is what you feel as an earthquake. Okay? So that's why I said energy has so many different transformations. So if you look at this in terms of, so you can have a change in kinetic energy. You could have a change in gravitational potential energy. How high do I lift ET? The higher I lift him, the more potential energy that I store. When I let go of him, that's going to change into kinetic energy. So, because so many things can be equal to each other, so like work can be equal to force times distance, which can be change in kinetic energy, which can be K minus K naught. So, you're going to have a question on your assignment dealing with a train. If you get the same answer again and again and again and again and again, don't worry about it because so many things can be equal to each other. Okay? So just keep that in mind when you get to the train question. Okay, kids, I am done. So I've sent out the lecture notes. I've sent out the assignment. If you want to retake that momentum test, I'm not going to go through the hassle of getting that ready unless someone tells me that they want to. Otherwise, I'm not. So if you want to retake that test, which is up to you, that's cool. I can write another one. But I'm not going to go through that hassle unless somebody wants me to. So if you're going to do that, that needs to happen this week. So, anyway, so the donations, like I said, Mr. Fulton and Miss Doan, you're now up to $150. So still behind my third block class, but at least you're there. Okay, kids, peace out. And maintain that energy. And I will talk to you all tomorrow.